fluid mechanics aspect so far, right? So Sumesh has been teaching about flow through pipes, flow between cylinders and things like that, and he ended up with talking about friction factor. So he's going to come back in about five weeks, and then he's going to do a little bit more of friction factor and few other things like boundary layer flows and turbulence and things like that. Okay, you're gonna see me for the next 5 weeks, and we're going to talk a little bit about particles. Okay, so what happens if you have particles in a fluid? Okay, that's the portion that I'm going to cover. So for today's lecture, I just want to do a brief introduction. Okay, that's the purpose of today's lecture. So the objective is twofold. I just want to introduce you to fluid particle systems. Okay, that's objective one for today's class. The second thing is I'm going to talk a little bit about fluid particle operations. Okay, so at least these operations, I mean, I think it's also there in the, if you look at the course contents, if you have gone through, I don't know how many of you gone through the course content, but if you've gone through, you'll see that I'm going to discuss some of the terms that are there in the course content in terms of what we're going to look at in terms of the fluid particle operations. Okay, just to begin with, particles are kind of everywhere, right? You look at any chemical industry or any industry in general, you will always have particles, right? I mean, you have particles are kind of dealt with in different forms, as listed here. You can either work with particles in the dry form. Okay, there's a lot of interest in looking at powders, processing of powders, how do you handle them, aspects of that sort. You also have cases where the particles are kind of processed in a wet form. Okay, for example, paste, things like that. Okay, and more often people work with the particles dispersed in a fluid. Okay, that's the last two things. Okay, you will come across something called as slurries. Okay, which is basically a dispersion of solid particles in a fluid. Only thing is when the particle size is coarse, okay, larger sized particles, maybe tens of microns or several or millimeter sized objects in a fluid, that's when you kind of think about something called as a slurries. You also have something called as dispersions, which typically refers to fine particles dispersed in the fluid. Okay, more of buzzwords, if you want to call it as, you can think about something called as colloidal or nanoparticle, okay, dispersions. Okay, that's okay. So what we're going to do in the rest of the 5 weeks is that we're going to look at how do people handle particles when you're going to put them in a liquid. Okay, that's going to be the goal of the next few lectures. Okay, any examples of fluid particle systems you know of? Some examples that I just want to list different fluid particle system that you kind of know. Yeah, some names. I'm sure all of you know this. Let's write some examples, right? How about paint? Right? Paint is typically, you have some solid particles dispersed in a fluid. Of course, there will be other additives like pigments and stuff like that, but definitely there are some fillers, and these fillers are going to be in the form of particles, and therefore paint is an example of a fluid particle system. Okay, any other examples? What is that? Aerosol is a, yeah, aerosol is a kind of fluid particle system, yes. How about milk? Right? Milk essentially has about a lot of water, plus there are some casein micelles, there are some proteins and stuff like that. Okay, that's an example of a fluid particle system. How about blood? Right, you have RBCs, there is plasma, right? So I can really think of a lot of examples where particles coexist along with the fluid, right? what is common between paint, milk and blood? What is that? Okay, I don't know if you can really call colloid as a blood as a colloid, because typical definition of colloids is that you should have a particle size ranging from 1 nanometer to about 1 micrometer. If the size of the particles are in that range, that's when they are called as a colloidal dispersions or nanoparticle dispersion. But if you look at blood, okay, the size of the red blood cells is larger. It's about 8 microns in size, so it's really not a colloidal dispersion. But still, there's something that is common between 1, 3, and 4, that is paint, milk, and blood. What is that? They're not emulsions. No, I mean, if you look at blood, it's not an emulsion. We'll come back to some of the classification a little later on. But what is common between the three is that the dispersing medium, okay, they're all particles in a fluid, right? And in this case, fluid is a liquid. Okay, if you look at all these things, these are particulate dispersions in a liquid, right? That's a common thing between 1, 3, and 4, right? Now, depending upon the fluid particle combination that you're going to work with, there are several ways that people classify fluid particle systems. So that kind of classification is given in this. What you're seeing, the picture is a cartoon to say that there is something called as a dispersed phase. Okay, it could be your it's your particulate matter, and there's something called as a continuous fluid. And this continuous fluid, if you want to call it as, you can call it as a carrier fluid or solvent. People use different terms. So there's a table here. So if you look at the continuous phase, right? The continuous phase can be gas, okay, and your continuous phase can be a liquid, okay. So and your dispersed phase can again be liquid, solid, or gas, okay, depending upon what kind of system that you're working with. You can have, if you have a liquid droplets dispersed in gas, or if you have a solid particles dispersed in gas, okay, you have what is called as a aerosols, right? And again, aerosol research is again there's a lot of importance now, because a lot of pollution, stuff like that, right? So examples of aerosols would be your fog, smog, smoke, okay. So all of these are examples of aerosols. Now, when you have a liquid as a continuous phase, and if your dispersed phase is gas, okay, you have what is called as a foam, right? All of you are familiar with foam, right? I mean, if you take a bucket of water, with some surfactant or some soap, if you open your tap, okay, water, falls in, and there's a generation of bubbles, right? So that's an example where, you have gas, okay, or air bubbles in this case, dispersed in a continuous liquid medium. That's an example of a foam. You have what are called as liquid and liquid dispersions, okay. Examples are, they are commonly called as emulsions, okay. As somebody said, milk is an example of an emulsion. There are a lot of skin cream, there are a lot of 2-in-1 shampoos. These are all examples of liquid and liquid dispersions, okay, also called emulsions. So you also have cases where you have solid particles in a liquid, okay. Typically they're called as a sol, okay, and examples would be your ink, muddy water, paint, and things like that, okay. So now that we know a little bit about fluid particle systems, and there are different examples, let's think about I have a question, okay, to ask, okay. Can you think of an example where the formation of particle occurs during a processing operation or unit operations, whatever that you can think of? Any examples? I want an answer. So far, we looked at milk and paint and stuff like that, right? So when people, of course, milk and blood is naturally occurring, so there are particles inherently in the fluid, right? And if you look at, like, say, paint is a formulation wherein what you do is there are particles, you put these particles into a fluid and you basically make a formulation to get a paint of whatever desired quality, right? Now these are examples where the particles are already either there or they're kind of dispersed externally, right? You take it from a, some source and put them into this fluid. Okay. I want an example where, do you think there are operations where the particles are formed during an operation, or are there cases where the particles are formed during an operation? It could be any chemical processes. Yeah. Grinding. Okay. So he is using a term called grinding. Grinding is typically, I hope all of you know grinding, right? I mean, it's basically what you do is you take a solid particle and you basically reduce the size. Okay, there are different ways of reducing the size, but if you chop off particles and make smaller stuff, right, that's what is called as a grinding. Okay, that's an operation where you start with a larger particle and you break it down into smaller size particles, right? I want an example for a case where I have a fluid, okay, and the particles are formed during its processing. Precipitation, right? Precipitation is one example. So one would be okay. So all of you have heard this word called precipitation, right? This typically happens, when you have, if a fluid becomes, in a loose term, if the fluid becomes insoluble for the particle, right? If I have, like, say, a solution, for example, water plus some particles, right? Or say that I have some salt or something dissolved in a fluid, right? And if I have a way of changing the solvent quality, okay, let me take an example. Okay, precipitation actually is again one of the areas where there's a lot of research. I'm going to give an example where precipitation is used as a method, okay, for making particles. Okay, there's a class of technique called nano precipitation. Okay, what is done is this. Okay, what you do is you take a container. Okay, your container has water. Okay, and what you do is you take another solution where you have some solvent, and in the solvent you dissolve a polymer. Okay, this solvent is a good solvent for the polymer. This polymer completely dissolves in the fluid, and it gives you a clear homogeneous polymer solution. Now, when I add this into water, if the solvent and water they mix, okay, they like each other, and if the polymer doesn't like to be in contact with water, as soon as I add this solution into water, what happens is this polymer kind of separates out, okay, and it separates out in the form of a particle. Okay, this technique is what is called as a nano precipitation. Again, one of the widely used techniques for making drug particles and things like that. Okay, so one of the examples where the particles can be formed during your operations could be nano precipitation. Any other example? Chemical reactions as well, right? So you can have chemical, okay, reactions, right? You can have a reactant A plus B giving rise to some product, and the formation of the product could be in terms of chemical reactions and during the reactions. Any other thing? Something that all of you know? Crystallization, right? Crystallization, again, another process where whenever there's a homogeneous fluid, if you create some sort of supersaturation, right? So there's going to be nucleation of particles and stuff like that, right? Now I'm going to tell you an example where particle formation occurs during flowing of a fluid. Okay, I'm going to take a case of a transportation of crude oil. What can you say from the images that you see? That's actually a cross section of a pipe. So in this pipe there was a crude oil that was flowing, okay, and at some point, they have cut the pipe and they have taken a picture, okay. What can you say from this image? So that's your pipe wall, right? This is your wall. Okay. What is in the center? Any guess? What is that? Any guess? Okay, that's your wax deposition. Okay, so all of you know that this crude oil is a complex mixture, right? It has hydrocarbons, paraffins, there is aromatic stuff, there is asphaltenes and things like that. Okay, there are organic compounds of different molecular weight present in the fluid. Okay, and what happens when you're transporting these fluids is that depending upon several conditions, this crude oil could be subject to different conditions. There could be cases where the temperature, okay, during its transport, temperature around the pipe could reduce, typically, right? It depends on weather conditions, right? There are some like say cases where the weather conditions are hot, cold and stuff like that, right? Now because you have molecules of different molecular weight, right, long chain molecules in the crude oil, what happens is that when you cool such fluid, okay, there's going to be some sort of crystallization. So what you are actually looking at is images which are obtained by taking an oil, and in this oil some wax is dissolved, okay, and then you heat this whole fluid into a high temperature, maybe like say 80 degrees centigrade, right? Now if we start cooling it down, at some point you start seeing the formation of these needle like structures, okay, and these needle like structures are the wax crystals, okay, and that are formed whenever you take this fluid and then cool it down to a temperature, something called as a wax appearance temperature, okay. So typically if there is a way of transporting fluid, this crude oil, under conditions where the temperature is always above the wax appearance temperature, it will continue to flow like a nice fluid, there is no issues. But the moment the temperatures surrounding this pipeline goes down below this wax appearance temperature, you suddenly start seeing the formation of these crystals, and eventually these crystals, what they do is they start depositing on the walls, okay, the inner wall of the pipes, and then the skin of the wax that is deposited, it basically grows in time, and ultimately it may even lead to a blockage, okay. This is an example where you start with pumping a fluid or transportation of a fluid, and then your particles are formed during its transport because of the fact that the temperature conditions are kind of altered during their flow. Now what do you think would be the implications of the formation of deposition of particles in terms of fluid mechanics? Any thoughts? Okay, so of course there are several implications, right? Now we know that whenever you have there is a generation of particles, the viscosity of the fluid goes up, right? We kind of saw an example in the previous in one of the lecture that I gave, wherein you have a base fluid, okay, you start adding particles. We said that the viscosity was going up, right? Therefore the generation of particles can lead to significant increase in the viscosity of the fluid. Therefore there is going to be associated transportation costs, so one has to be worrying about that. As it is evident from the figures, the deposition of the particle on the inner wall, it reduces the cross sectional area, right? Effectively the cross sectional area that is available for the fluid flow is going to reduce, therefore is also going to be, there is going to be a reduction in the the flow rate as well. Okay, so it could have implications on the fluid processing that you're trying to do. Of course, the too much of wax deposition can lead to blockage. It can completely stop the fluid from transportation, right? And so we, in the previous lecture, we talked about the skin friction and form friction, right? And we said that skin friction basically comes from the roughness that is on the inner wall of the transport, the fluid, the pipe through which the fluid is being transported, right? Now, when you have wax deposited, obviously it's going to affect the surface properties, right? And therefore it is also going to affect the skin friction. So therefore, so the formation of particle has is of relevance both in terms of trying to understand when do the particles form, plus as well as to to look at fluid mechanical aspects in terms of yeah, somebody has a question. The first point. First point, were you there for one of the class that I talked about viscosity measurements? Okay, so let me just draw something here. So we had basically discussed about a particular plot, where the viscosity, okay, was measured as a function of say shear stress. Okay, wherein what we said that the viscosity would remain constant as a function of shear stress when you have case where you only have a fluid. Okay, now I put in a small amount of particles. What happens? The viscosity goes up. Okay, now the increase in the viscosity purely comes from because of the fact that there is some dispersed species in the fluid. Okay, therefore the viscosity can increase. Of course, when you want to pump a fluid that has a higher viscosity, of course, you would have to worry about the pumping costs associated with the fluid particle system. Okay, so in that context, the formation of particles, depending upon what is the concentration of particles that are being generated, it can significantly increase the viscosity, and that could in turn have effect on the transportation in terms of the pump requirements and things like that. There are two aspects. Okay, in the example that I gave you, it so happened that initial stages of wax crystal formation, the example that I gave, when these things start appearing, initially they are nicely dispersed in the fluid. Okay, in that context, I have a fluid particle system, right? A homogeneous fluid particle system. What you are seeing here in terms of deposition happens at a little later stage. Okay, first there's going to be some formation of first layer of wax crystal. Okay, so it's not that this happens instantaneously. Okay, it happens during a period of time, but initially you could think about crude oil, at least when the temperature are around this wax separation temperature, is a homogeneous dispersion of such particles in a fluid. Okay. Okay. So now, okay. So at least with this, I just want to set a base for just to say something about particles, and that there is some particle fluid systems, and there can be some implications in terms of understanding their fluid mechanics. Okay. Now I'm going to now I want to move on to talk about the different fluid particle process that we're going to see in the course. Okay, I just want to start by showing you a video. Let me just show that. Okay, so what you're seeing is a movie. Okay, we can do this in our lab if you want. If you're interested, we can do that. So what is done is they have a container, and the container is filled with water to begin with, and all that is being done is take one drop of milk, okay, and just drop it in the fluid. Okay, nothing else is happening. Okay, just one drop of milk into a container, and it is being kept below a microscope objective, and you're watching it. Okay, what do you see? Oops, I should go back. Right, you saw the title, right? What do you see? Brownian motion, right? Okay, right? This happens when the particles are tiny. Okay, when you have a very tiny particle. Okay, if I do the same thing, like say, let's say, I have a container, I put in millimeter sized objects. Okay, larger stuff, I put in a liquid. This won't happen, right? That's because the particles are really large. Now the reason why this motion happens, because there are solvent molecules that are hitting the particles, right? Whatever thing that you are jiggling around, that is because there are solvent molecules which are continuously hitting the particle, okay, and the continuous bombardment of the particle and the solvent molecule is what is leading to this motion, okay. And this motion happens when the particles are small enough, okay, and if I progressively increase the size of the particle, you will see that very tiny stuff can move a lot. Make it a little bigger, it moves a little less, okay. If I make it a little bit more bigger, it won't move, okay. That's because the energy with which the molecules are hitting the particles may become much larger than, much smaller than what is required to move the particle when the particle size becomes larger, okay. So let's put it that way at this point. So we're going to look at in the context of the course, we're going to look at some examples where we're going to have a fluid, and we're going to set the particle into motion, okay. In this case, motion happens purely because of the bombardment of solvent molecules with the particle, but there are other ways of setting a motion of the particle, right? Can you think of other ways of I have a fluid that contains particles, I would like to have them move. Any examples? Any you can temperature increase will, I don't know if that's the best way to answer this, because if you have like say a tube, for example, okay, and say that I have this tube contains fluid and particle. If I heat one end, if I cool the other end, then there's going to be a temperature gradient, right? Okay, now because of this temperature gradient, the things can move. That is what is called as a thermophoresis. Right? What we saw just now is an example of, okay. Any other examples of how to make them move? What is that? Somebody says electrophoresis. Okay, as the name itself says, in this case you can set the particle into motion by applying an electric field, right? How about something called the diffusophoresis? Okay, wherein basically the motion is set by creating a concentration gradient, right? So we are going to look at some aspects of this in the course, okay. I'm going to have 1 or 2 classes on looking at particle characterization, okay, because before you start looking at a fluid particle system, you should have an idea about what is a particle, okay, where do they come from, what is the typical characterization that one has to do before you work with fluid particle systems. So I'm going to have some aspects of that in the course. We're going to talk a little bit about something called as a Stokes-Einstein relationship, which basically comes from the Brownian motion aspects. Okay, we'll talk a little bit more about it in the course. Some aspects of electrophoresis, just to give you an idea about motion of particles in a fluid. Okay, that's going to be the few aspects. Now, some aspect that we're going to look at in the course is to look at if I have a fluid particle system, how do we separate particles? Okay, so any thoughts? Like say, imagine, let's think about a case. Okay, I have a container. Okay, say that this container has say water. Okay, and take say it's a muddy water. okay, or a rainwater if you want to call it as, okay. There are a lot of particles in it, right? So you have a, okay, so you can think about this as maybe a clay particles, right? Because when you get rainwater, okay, a lot of clay particles will be present in water. So if I want to, like say, separate these things, what do you think would be the best way to do it? So what I would like to do is to take this and then somehow ensure that everything is at the bottom and there's a clear fluid. So how do you do that? Any example? Any thoughts? Right? Something called the sedimentation. All you have to do is take this container which has these particles and just let it stand, okay. Then what is going to happen is your gravity is going to kick in, okay, and the particles are going to slowly sediment to the bottom. So we're going to look at some aspects where we're going to look at sedimentation of single particles, okay. We're also going to look at sedimentation of collection of particles, okay. So in this example, I mentioned that they're going to settle down because of gravity, right? So are there other ways of inducing sedimentation? Are there other ways by which I can separate out the particles, right? In this case, what you can do is you can use what is that? You can do coagulation as well. Yeah, somebody says coagulation. So what it basically means, what he is trying to say is that I have a system like this, okay. What I'm going to do is whatever particles I have, I'm going to make them agglomerate or coagulate. What happens when they agglomerate or coagulate? The particles are going to become larger, and when things become larger, they can settle, right? So you can do that. And the point that I wanted to say was that instead of gravity, I can use an external field, right? I can use what is called as a centrifugal forces, okay, or your electric or magnetic forces, right? I can, so there are ways by which I can either exploit gravity for, separation of particles, or I can use some external fields. So we're going to look at some aspects of that in the course, okay. We're going to start with talking about settling of single particles, okay. There's something called as a free settling that will happen when the particle concentration is lower, or when you have maybe very few particles in the dispersion, okay. That's your free settling. And hindered settling when you have really large number of particles, okay. We're going to look at some aspects of that. Then we will move on to settling of slurries, where you have a dispersion of particles but concentration is really large, okay. And people do something called as a batch sedimentation test. These are kind of tests where you take dispersions in a column, long column, and you basically watch them, okay, as the particles settle. Indeed, you have an experiment in the next semester where you're going to do something called as a batch sedimentation test to look at the sedimentation behavior of slurries. So we're going to do some of that, and we'll talk about some aspects of using external field for okay. So now, so in processing, you often come across cases where I would like to have a fluid particle contact, okay. What I mean by that is, say that I have a particle, okay. Now I would like to pass maybe a stream of say liquid or a gas over it, okay, there are certain devices for doing this, okay. Can you think of examples where I want something like this to happen? I have, let's think about, like say, solid catalyzed reactions. Right? So when you have something like A plus B going to C, okay, if this reaction happens on a catalyst surface, okay, therefore you would like to have a catalyst. I would like to hold it in this place, maybe by some means, and I would like to have the stream of A come in, stream of B come in, and I would like to have the contact between the two occurring on the catalyst surface, and and that would lead to some reactions, right? So there are a lot of processes in chemical engineering where you have to ensure a proper liquid solid contact or a liquid gas solid contact. Okay, you can have a two-phase system where I'm talking about liquid, okay, I'm talking about a liquid solid contact, okay, or a gas solid contact, or a liquid plus gas solid contact, okay. And there are devices for doing that, okay. And one of the very commonly used device is something called as a packed bed, okay. It's a fairly simple setup. What you have is basically a long column, okay, and in the column, right, the region that is marked, you see these spherical things, okay, these are particles. These are kind of put in the column, okay. That's what is called as a packed bed, right? It's a solid particles, packed into a bed, okay. And then in this particular example, what you have is basically there is a liquid that is coming out. So basically there is a scrubbing liquid, and this scrubbing liquid is okay, let me put it this way. At the bottom there is an entry for something called a contaminated gas, okay. This gas contains some liquid droplets, okay. The objective is to have a clean gas go out at the top, okay, and whatever gas that is entrained, okay, that is there in the whatever liquid that is entrained in the gas, I want to take it out, okay. What I do is I introduce a liquid, and what this liquid does when it is coming down the column is that it will take out all the liquid that is coming along with the gas, right, okay. And when it comes down, okay, it takes out all the liquid, so that the clean gas can go out, okay. So there are such devices. Of course, in this case it is used for some kind of a mass transfer operation, right. So you basically want to transfer the liquid that is there in the gas stream that is entering, okay. I want to transfer that into a liquid stream that is basically coming down, right. So now if you were to do this without the packed bed, is very hard, right, because of course the gas will go up, okay, and your liquid that's coming from the top would come down, right, but a proper contact between the liquid and the gas is not going to happen, right. Therefore when these fluids flow through the packed bed, okay, this when I say packed bed, this is a bed of particles. Of course there's going to be gap between the particles, right, and when things flow between these gaps, right, so there's going to be a proper liquid gas contact in this case, okay, right. So therefore there are cases where you want to ensure either a liquid contact, liquid gas contact, or a liquid particle or gas particle, okay, all kinds of fluid particle operations where you want to ensure a proper contact between different species. People use this concept called packed beds. We're going to look at a little bit more of that in the lecture. Now the other examples where one could look at ensuring a good contact between the particle and the fluids is by something called as a fluidized bed. Okay, so what you're looking at is basically a case where on the left again you have a column, and all these particles are kind of packed into a bed. Okay, now what you do is if you increase the velocity. Okay, so I just wanted to say that in the packed bed what happens, what keeps the packed bed in that packed bed configuration is that there are basically support plates. Okay, there are two plates that are basically holding these particles, and no matter what kind of fluid velocities you use, the particles are going to be in a fixed state. Okay, now if you have a fluidized bed, if you remove the top plate, the top plate is not there anymore. If I go on increasing the velocity of the fluid that I'm sending from the bottom, at some point they're going to be in a nice dispersed state, right? That is what is called as a fluidized bed. So we're going to look at some aspects of that. So we're going to look at flow through packed beds and fluidized beds. We're going to analyze flow through packed bed in terms of, we've learned flow through pipes. Okay, we're going to use that concept to look at flow through packed beds, and then look at some pressure drop and things like that. So I have again a nice video. If you in pharmaceutical industry, there's a need for looking at coating drug particles. Okay, and coating of drug particles can be done for several reasons. One of the reasons could be that I would like to control the release, right? So if I have people talk about controlled release, right? One of the way of controlling the release is that I have a particle and I do a coating on the surface. Okay, or this is a case where there's some kind of a agglomeration that somebody was talking about. It's a process called granulation. Okay, that means you start with smaller particles and then you kind of induce some sort of aggregation between the particles. Okay, fluidized beds are used for granulation purposes. Okay, what you do is you have a packed bed to start with. Okay, and then you introduce some gas, and then introduce some way of joining the particles. This is another example where fluidized bed is being used for coating applications. So you fluidize a bed to begin with, and then whatever coating material that you want to put on the surface, you again put it as another fluid, and then you can ensure a nice homogeneous uniform coating of the stuff on the particle surface. So the idea would be to make this core shell kind of particle, where the core is your maybe a drug molecule, for example, drug particle, and then your and the coating could be something that you're trying to use for controlling the release. Okay, I just want to end by the last one piece. So we talked about separation by sedimentation and and using external forces, right? Any other ways of separation you can think of? Have you heard of an operation called filtration? Right? Okay, if you have, I'm sure all of you may have seen a water filter, right? If you look at water purifier, there's a pre-filter that takes water from tap, and it removes some particles to begin with. It goes into a purifier. There are going to be some carbon filters and things like that, right? So we are also going to look at some aspects of filtration during the course. Look at types of filtration. There are some specific types of filtration, something like the constant rate filtration and constant pressure filtration, filtration devices. We're going to look at analyzing filtration in the context of flow through packed beds. Okay, so these are some of the things that we're going to do in the class. Okay.